This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development.
The last speaker for the year is Chuck Moore. He's CTO at AMD. He's going to talk about multiple cores, a topic we're all somewhat familiar with, but I'm sure he has a different perspective. Before being at AMD, he was at IBM. He worked on the Power 4 and other processors, and has come to see the light and come to California where it's interesting and warm. Chuck?
Okay, so I should correct one thing. I'm actually not the CTO, but I play one on TV. So. Well, thank you.
At least you have a virtual one.
Yeah, that's right. Well, thank you for coming out. I know it's the last day of classes, and sitting outside on the bench in the sun, it was pretty hard for me to come in here. So I do appreciate your taking the time. Today I wanted to talk to you about a project that I'm working on at AMD called accelerated computing. And as we all know, we're in this so-called multi-core era. And what I want to do is build the case for accelerated computing in this multi-core era. So the way I'm going to start out is by talking about Moore's Law, Uncle Gordon. He's not really my uncle, but I like to pretend that too sometimes. And go through some high-level trends that have sort of led us to the place we're at. Hopefully this is all going to be review for you guys, but I think it helps motivate some of the things that lead me to my conclusion. Then I want to talk a little bit about throughput computing, because there's an awful lot going on in this area as well. And it turns out there's a relationship between throughput computing and what I call accelerated computing. Then I'll talk about a couple of the challenges in accelerated computing. There's certainly more than just the two I've listed here, but these are the ones I'm going to zero in on and then wrap up with a summary. So Gordon Moore, back in 1965, of course, wrote this seminal article where he observed that we were seeing a doubling of transistor density every 18 months. And he projected that we ought to continue seeing that into the future, and of course he was right. But another trend often confused with Moore's Law is this idea that you get to double the performance every 18 months. Now, as it turns out, we often have been able to do that. But really, this is an example of ongoing customer value that results from the integration capabilities that Moore's Law brings to the industry. And in fact, the industry is dependent on this ongoing customer value. We need to build parts that offer value. We exchange them for money. And with that money, we're able to develop new process nodes. We're able to build new fabs. We're able to actually do new designs. And then we're able to build them and sell them. If that virtuous cycle breaks down in any form, whether it be because we can't build the technology or because we can't add value, this industry is going to be a very, very different place. So what I would contend is the question we should all be asking ourselves, is how do we continue increasing customer value? So a few high-level thoughts to start with. Of course, Moore's Law looks something like this on a log scale, kind of shows where we're at. The good news is it keeps going. My technology counterparts at AMD tell me, we've got a fairly long ways to go here on Moore's Law, which is nice. However, there's some big new challenges. Design for manufacturability is a big issue, variability, the reliability of the devices, all these things are coming into play. Similarly, the power wall, so-called power wall. Over the past 10 or 15 years, we've seen this incredible run-up in the amount of power each socket is allocated. We call that the TDP, or thermal design point. And what happened a few years ago is it got so high, it was causing incredible expense at the system level, so it flattened out at maybe 120 watts or so. But now what we're seeing is it's starting to get pressured down. And it's starting to get pressured down on behalf of all markets. Server, because by the time you deploy hundreds of servers, you're talking about some real serious money here dedicated to power. In fact, the cost of ownership easily outpaces the total cost of the hardware. Desktop, what you want to do is you want to eliminate fans. You want to get to those nice new form factors that we've seen in the market that really are selling well. So those beige boxes under your desk, that's kind of a thing of the past. And in terms of mobile, of course, it has to do with battery life. So the frequency wall, one of the ways we were able to get performance over the past 10 years or so is by massively increasing the frequency. And the way we did that was partially because of the technology and the raw speed of the transistors, but also because we were doing deeper and deeper pipelining. As it turns out, of course, there's a point of diminishing returns with deeper and deeper pipelining. And different people have flirted with that level. We could debate where it is, but I think it's around the 15 or 16 FO4 delays per pipeline stage. And after that, you don't get much more frequency from pipelining. And even if you do get the frequency, you're actually bending over in performance. Complexity wall. Here, IPC is the efficiency or instructions per cycle that you're actually able to get out of a program, and issue width is the number of instructions you issue. It turns out we can build machines that have wider issue. Say today, many machines have 4 issue. We know how to build 8 issue machines, but the problem is the complexity is exponential and the gain is logarithmic. So it's a very nasty confluence of realities there. So notice nobody's building those kind of machines. Locality, again, everybody should understand this. This is the basics of cache size. Yeah, you can get more performance by doubling the cache, but the amount of performance you're talking about is 5–7% once you have an adequate cache. You're not really offering significant value, but cache is a big amount of area to throw at the problem. So that's a point of diminishing returns. So what this means is single thread performance, when you sum all these things up, it's planing out. And I think we've seen that in the market. But more interestingly, we've seen some people making claims that it's time to take single thread performance down again, go into this regressive state. And I'm not so sure that's such a good idea, and I'll show you why in a few minutes. So going back to my original supposition, well, what do you do? How do you add customer value? Well, it turns out customer value is a funny thing. And it's sometimes not as intuitive as you would like. And I show this as an example. Here there's 2 systems that were taken off an unstated website on the internet from January 2008. So there's 2 systems here, and I configured them identically. So the question is, what's the difference between these 2? And it's not a trick question, really. And the answer is one is black plastic and one is white plastic, and the price is $125 more. Black costs you $125 more. But even more telling is this little factoid. You can get the white one with a 10% performance drop for $125 less. Therefore, black plastic is about the same value as 10% frequency. That's the customer equation that's playing out there right now. So you got to kind of take that into account. As an architect and a microprocessor designer, I'm all about the performance, but there's a platform level play here, and what does the end user get? Especially in this PC space, what does the end user get is really the name of the game.
By the way, do you know why black is more expensive? Anybody know?
Style.
What?
Style.
The question was, why is black more expensive? Why?
Why should 20% difference in performance of a 2 gigahertz processor cost $125?
Well, there's that question too, but why is it equal to black plastic? Is it, I don't know, is there graphite in there or something? There's no good reason.
To do a better job.
It's style.
Just maybe quantity.
So AMD, just to throw a little plug for AMD here, is, before I joined AMD, they came to realize that there was diminishing performance in the single core regime. So with the Opteron line of products, they started investing in things like integrated memory controllers and glueless MP with these hypertransport links, 64-bit capability, and adding the capability of putting 2 cores down into the same socket, and that was architected it up front. Those were all really solid ideas, and it turns out they really resonated with customers, and Opteron was a real success story. Following that up, there's a quad-core version. We call it the native quad-core Barcelona processor. Again, it has this seamless upgradability. Virtualization, it turns out, and improving the performance of virtualization is very, very important to server customers who are buying these high-end chips. So improving that was a real goal of this design, as well as improving the performance per watt. Because now that TDP, that used to be shared by 2 processors, is now shared by 4. So you've got to improve the inherent performance per watt of each core, or you're dropping the performance significantly. So from that, you might say, oh, okay, Chuck's saying that SMP and multi-core, that's the answer. That's the customer value story. Well, you know, I'm not so sure, actually. In the near term, there's definitely potential with chip multiprocessing and SMPs in general. Commodity multi-core processors sort of break the chicken and egg. Hopefully all of the students here have access to multi-core processors already, which is great. That may inspire you to try to write parallel programs. That would be great. But you're going to find out it's kind of hard. There's an impressive amount of research firing up to get that going. In fact, there's a new lab here at Stanford called the Stanford Pervasive Parallel Lab, that recently got kicked off that looks great. I mean, there's a lot of good stuff being talked about there. So some workloads, maybe we'll be able to get something out of these, but on other workloads, I'm not so sure, because Amdahl's law seriously inhibits unstructured parallelism. And again, in the interest of review, you know, there's this friend of mine at IBM that once said everybody knows Amdahl's law but quickly forgets, because it's got this funny little characteristic that you'll resonate with in a minute, but maybe the implication of it doesn't always dawn on people. So here's that very, very, very simple version of Amdahl's law that says SW is the percentage of serial work. Therefore, 1 minus SW is the amount of parallel work. You can divide the parallel work by n, which is the number of processors, invert it, and you get the speed up. So, for example, if there's no parallel work at all, it's 100% serial work, you get that black line. Right? You don't get any speed up on your application because there's no parallel work to be done. If it's 100% parallel, you get that wonderful green line. You know, for 8 processors, you get 8x the performance. Well, what happens when you actually do have some amount of serial, right? That's the kind of the interesting case. So here I've plotted 10% and 35%. And, you know, at first thought, it's like, well, maybe that's not so bad. You know, that doesn't look so bad, you know, the 10% or the 35% even. But it turns out it's that 35% one that kind of caused Gene Amdahl to sort of state Amdahl's law. Because if you think about it, 35% serial means that red line never goes beyond 3. If you take n to infinity, right, it never goes beyond 3. In fact, if you zoom in a bit on those lines, they look like that. So again, everybody knows Amdahl's law, but sometimes it kind of escapes us, and we forget just how pervasive of an effect this has on our ability to get speed up out of parallel processors. Hold that thought. Now, kind of taking it to the next level, in reality, it's not just Amdahl's law that we got to worry about. It's what I was talking about earlier. You have a socket, and you have a fixed amount of area and a fixed amount of power in that socket. And the question is, what are you going to put in that socket? So for example, here, if we had a chip that had 200 square millimeters for cores and 80 watts for cores, maybe the chip is actually 300. You got some for an L3 cache. You got some for the PHYs or whatnot, memory controllers. 80 watts, well, maybe 20 of it's for clocking and the PHYs or whatnot. But you've got 280 for the CPUs. So based on that, you can start to talk about different size CPUs. Tiny CPUs, small CPUs, medium, large. And you know, there is a method to the madness on how I did the numbers here, but a nice kind of commodity processor today, you know, an Opteron style processor, might call that P equals 1 and call it 25 square millimeters. So therefore you can fit 8 of them on a die in that 200 square millimeters, and each one gets 10 watts. Okay, now you've heard about these 100 core chips and a lot of interest in 100 core CMPs. Well, if you want 100 cores, you know, you got to divide that out, and what you end up with is about, you know, 1.5 square millimeters per core. But more telling, you get about 0.6 watts per core. And as it turns out, that's not enough area to do a decent job on performance, and that's not enough power to do a decent job on performance. So the uni performance on that core goes way down. So this little core is very constrained on performance. So by the time you plot that out, so this is sort of the area and power on top of Amdahl's law, what you see is, geez, it's not at all clear that deploying a whole bunch of small cores is a good idea at all, especially when you take into account area and power constraints.
What about the power on the interconnect? That
Yep.
as you get more and more processors, more and more of the,
Yep.
the system
I-
logic is sort of spread across.
I actually think I was incredibly generous on the tiny core here. Okay, so building on the rest of this chart that I started a minute ago. So you might say, yeah, okay, I understand that it's difficult, that Amdahl's law is a difficult thing to deal with. But it also turns out that existing software really isn't that soft. So even if you really wanted to attack this problem, today's workloads, you're not going to go in and rewrite today's workloads. Nobody does that. You add features, sure, that'll add value, but you don't go in and rewrite the programs because transitioning the concurrency model underneath these is really hard. So then you say, what about the new, okay, we're going to write new applications that are all parallel. Well, that's good, but it turns out that many of the applications you actually want to write have some new characteristics, some interesting new characteristics, one of which is they want to operate on different kinds of data than you're used to thinking about. They want to operate on media-rich content, things like HD video streams or image files or audio files or XML encapsulated command files that are all compressed and things like that. So it turns out that when operating on those kind of data types, traditional processors don't do that well. They're just spinning their wheels dealing with that kind of data type. So it's not clear that even when you write new applications, you want to write them in a parallel way that goes after this, after a CMP. So in reality, I think that these SMP, chip multiprocessor, and symmetric multiprocessor programming challenges are just an early indicator of more important shifts yet to come. So what I'd hate to see is the industry focus on, or the academic community focus on solving the multi-core programming problem and ignore the idea that, well, in reality, those multi-cores are going to become performance heterogeneous. There's very little doubt about that. If nothing else, based on power management, cores are going to have different capabilities. As you add more cores, the issue of synchronization and the issue of non-uniform resource management. This core has closer access to the L3 or to memory or what have you. That stuff starts to get exposed. So in some sense, there's a bigger problem related to resource management and scheduling that needs to be dealt with as we deal with the multi-core challenge. Okay, so getting to your question, I think. So throughput computing. So I've said a lot about parallel applications, but let's face it, not many of us are running parallel applications, not many of us are writing them. In reality, what we're interested in is throughput. What do I mean by throughput? It's sort of, instead of turnaround time on getting one job done, the question is how long does it take me to get n jobs done? Because now I can start to play some games in terms of dealing with latency and so on. So intuitively, multiple cores and multiple threads should be faster than just one, sure. So in some sense, for basic multi-program throughput, your desktop PC, if you think about it, the OS is got a scheduler in it, and it schedules to multiple cores. So the OS kind of has a serial component to it, and it's scheduling different applications to different cores, and it's time multiplexing the use of those cores as well. And that works pretty well, up to 2 or 4, maybe even 8 processors. But at some point, the OS starts to get in the way, and the OS actually becomes the bottleneck. You won't get as much scalability as you think you might until the OS schedulers step up to some of those challenges I was referring to on the last slide. Furthermore, more advanced applications sometimes take on this role all into themselves. So for example, modern databases, they don't wait for the OS. They accept a bunch of resources and then they schedule it out themselves. And the reason they're doing that is because there's a lighter weight context switch capability, there's a lighter weight scheduling capability, and they're able to get substantially better scalability than when going through the OS all the time. This is why you can see some of those Oracle databases scaling so well, because in some sense Oracle has taken on the burden of the scheduling and the throughput themselves. Some HPC apps do this as well. And it turns out there's some types of web servers that do it. So what about large-scale throughput? Let's step back and take a look at that. So what do I mean by a large-scale throughput machine? Well, you know, a large-scale throughput machine would be characterized as you have far more threads than you have hardware slots. So maybe you've got thousands of threads that you want to run, but only n slots. Well, how do you deal with that? And the answer is what you do is you develop a centralized controller that works to dispatch and sort of juggle those threads and cover whatever latencies or whatever it is you're trying to cover up with multi-threading. So I've got two examples here, and they're on very opposite extremes. And you probably have your own examples, but here's two good examples, I think. One is you got this massive click stream coming at your web server, your two-tiered web server. And in essence, there's usually a big SMP or moderate-sized SMP that accepts that click stream and then sprays it out to a set of blade servers or other types of throughput engines. So in reality, what's going on here is it's a form of throughput, but it's kind of taken up a level, right? The click stream has enormous amounts of natural parallelism, and the question is how do you spray it out and keep it coordinated? This is what the two-tiered web server does. On the right here is a modern GPU. And if you really dig deep into how a GPU works, what's going on there is there's a piece of hardware called a sequencer. And what it does is it takes higher level commands about pixel processing or vertex processing or geometry or several others actually, and it turns them into large numbers of threads. Because in some sense, every pixel is independent. Every vertex is independent. So what the sequencer does is it helps spray out this work to a common set, what's becoming a common set of execution units within the GPU. Now there are still some fixed function units and other things that fill out the full rendering pipeline, but this, in essence, is how modern GPU works, and I would argue it is a throughput machine. In this case, the sequencer is a dedicated piece of hardware instead of a program, but it could be a program. So if you really think about it, what we've got going here on both these extremes is cooperative heterogeneous processing. So we're already dealing with this today.
So both of those examples use a single centralized controller, right? And so eventually you won't be able to scale your SMP server up big enough. Or you won't want to pay Sun or HP or IBM, whoever, enough. So it seems like there would be a lot of value in being able to distribute the sequencing, or generally the control handling up front.
Perhaps. Yeah, there's a scalability issue of the control of the centralized controller at some point. But this gets you that first layer of transactional throughput on the web server side, and it gets you that first layer of data parallel throughput on the CPU, on the GPU side. Now, notice also that there's a great deal of interest in generalizing the use of the GPU for other types of data parallel workload. If you want to do that, what you really have to do is you have to couch your problem in a way that matches this hardware. And that's why it's so darn hard to do it right now. Yes?
Well, what about the other side? After the blade servers, there are usually a database, which is again a centralized.
Yeah, no, that's a great point. In reality, many of these web and modern data center installations are more than two tiers. There are at least three, and there is a big database server on the back end. There is a scalability issue there, and I'm really not trying to talk about that here. I'm really just talking about the nature of throughput computing and how it's been really effectively deployed on the front end. The scalability of that back-end server is kind of a traditional issue, and it kind of goes to the database starts to take on some of the functions traditionally done by the OS and gets that next level of scalability, among other tricks. There's also distributed databases. Yes?
Looks to me like at least actually most of them, really rely on the ability to isolate threads and not require that they communicate with each other.
Absolutely.
And there's no shared data.
Absolutely. So when there is shared data and when there is communication, I would argue it's that parallel computing case I described in the first set of Amdahl's law slides, because that's what you're dealing with, is synchronizing and sharing, and that's part of the serial overhead.
Serial overhead.
Right. So this presumes there is no serial overhead, and look what happens. There's all kinds of interesting options that come into play. Okay, good. So yeah, as it turns out, the GPU is a good example of something we might, obviously there's a great deal of interest both in academia and in industry on making use of the GPU for more than doing just graphics. And why is that? It's it's not just the raw performance. It's the power, it's the performance per watt that's so extraordinarily better that really motivates this. Where we have an issue where we don't have as much power as we would like in the socket. So instead of deploying those last 2 cores, perhaps deploy a GPU and get a 20x speed up, performance per watt speed up on workloads that can make use of that type of data. And interestingly, this it says 1 teraflops in a crossfire configuration. Those numbers are going north very fast. So we're talking really multiple teraflops in very short order. So then maybe somebody was kind of getting to this at some point, that throughput, that centralized controller, doesn't that get in the way? What happens if that starts to get in the way? It can get backed up, and it effectively becomes a serial component in these topologies. Well, I hesitate to put in this slide in because I don't like beating up on competing products, but I think there is a real lesson here with, so this is a slightly critical look at the IBM Sony cell processor. It was designed to be a multimedia throughput machine. Fundamentally, that's what it was designed to be. And no doubt, those SPEs, those SIMD engines are incredibly powerful engines. But, something happened on the way to the ranch, and, there's that PowerPC core in there, and really it's too weak to act as the centralized controller for several reasons. First of all, when you transition code to run on a cell, you first have to kind of get it going on the PowerPC core, and then you migrate it to work on the SPEs. The PowerPC core isn't strong enough to carry the day. It's just not strong enough to carry the day. So you either port it and get to those SPEs immediately, or you don't port it. You don't get a product. The other thing is, the programming model and the exposed memory in some cases kind of made it difficult to program this machine. So I think there are lessons to be learned from, there's cautions out there about how to build decent throughput machines. So how would you build a better throughput machine? Start with a powerful, efficient uniprocessor. I like the idea of starting with a next generation Opteron, of course. Deploy 1 or more of these. Don't get skimpy. You still need to support legacy applications and excellent performance on them. And you want a core that can really be an outstanding centralized controller. Now start adding a large number of small, power-efficient, domain-optimized compute offload engines. That doesn't mean 10 or 20 different ones. It means get to something perhaps like a GPU that has extraordinary power efficiency advantages and deploy that instead of additional cores. Build an optimized memory system. If you don't feed these things, you don't get the performance. It's one thing to get peak numbers. Of course, it's something completely different to actually get anywhere close to that on real applications. Also, the communication and synchronization between the host, if you will, and these offload accelerators is very important as well. The other thing that's important is the programming model. You need an abstraction that favors simplicity and programmer productivity. It's hard enough programming homogeneous multiprocessors. If now we pile on and say, and by the way, the ISAs for the processors you're running on can be different. In some cases, they're not even programmable processors. That you can sort of blow a gasket if you're not careful with people on that. So there's got to be some new abstractions that are put in place that it perhaps costs a little bit of performance because you've got some layers in there now. But in return, they allow domain-specific programmers to get a lot more effective at expressing their programs and presumably, I think, getting at the parallelism. So what you get out of that is accelerated computing with heterogeneous processors. So, accelerated computing, the motivations for this, the reason, I'm excited about it and the reason I'm working on it right now is I honestly do believe that new and emerging applications are defining and operating on, much larger scale and more abstract data types. 1080p is a basic data type of the future for client devices. And it turns out that targeted special purpose hardware can offer substantially better power efficiency when operating on those data types than traditional processors. Traditional processor, when operating on 1080p, the first thing it does is mess up its whole cache hierarchy before it basically pumps it right back out to memory. There's just not a lot of processing versus data movement. So the way this would work is a traditional host would offload work to these dense compute accelerators. You would go through APIs or libraries or domain-specific libraries in some cases to avoid the heroic programming. You would use a concurrent runtime environment to ease some of the scheduling and resource management issues. And out of that, what starts to happen, and this is an interesting result, is what today the industry is sort of locked on ISA compatibility. You're either x86 compatible or you're not. But I think this line of thought leads to API and platform level compatibility, which is a really nice result for the entire industry. Now, arguably, maybe it's not so nice for AMD because we happen to have a very successful franchise with x86, but I just think this is absolutely inevitable, and I don't think we can fight it, so we're embracing it. Now, I do think the hosts in these systems will continue to be x86 processors. I don't think that will go away anytime soon. So accelerated computing is a platform for heterogeneous computing. So it's not such a crazy thought, really, because it's going on in other parts of the industry as we speak. Down in these low-end devices, I've got an iPhone in my bag here. It's got 3 ARM processors, but I don't know that it does. It's just acting like a device to me. But it turns out all these designs have heterogeneous processors in them. They have different types of accelerators and different types of processors. They do tend to be a little more embedded than the open programming systems that we offer today. But again, that's where some of these platform abstractions need to kick in. Here's an example of an AMD chip that I was not involved with, but it's basically I believe it's a set-top box kind of chip. And I was fascinated to see, there's a reasonably powerful MIPS CPU on here. I think it's maybe a 500 megahertz, 800 megahertz MIPS CPU. But all of these video and encode and decode accelerators and quality accelerators, security accelerators, all these things are on this little chip that you can buy for like $5. It's kind of an amazing deal. So it turns out there's not, this system doesn't happen to use all these things with massive concurrency involved. They're not all going at once. It sort of passes them between them is the model here, sort of like a pipeline. What we have in mind, of course, is more concurrency as well as differentiation of type. But the reason they have differentiation of type in this kind of design is for the same reason. It has to do with power. It actually costs them area, it costs them money, but it saves enormous power. All right, so moving on to some of the challenges. So the memory, bandwidth, and data movement challenges is actually pretty daunting. You've got to keep up with the computation rates or you really don't get the end result you're looking for. And I'll say more about that in a minute. The new and appropriate software stack and APIs. A programming model that builds on what people are doing with multi-core seems like the logical starting point. But again, I would argue you got to go another step or two beyond that. But I think they're less dramatic steps than the jump to multi-core. You want to use abstraction and trade off some of the performance that results from that for programmer productivity. In fact, I would argue programmer productivity is one of the top constraints facing architects today. And it didn't used to be that way. In fact, power is the other one. So in case you guys didn't know this, those are the two you should be carrying around. There's also, realistically, we can't go on and reinvent everything, right? The OS, we need to live within the bounds set by the ecosystem that the OS and some of the runtime environments create. So we don't get free rein to reinvent everything, but I think we do have free rein to build some new productivity layers above the traditional stuff. Another big challenge is managing the context state and exceptions. All of a sudden, if you start offloading to accelerators and then say you get a page fault over there, there's a lot of outstanding state that you may have to collect up and save. And that turns out to be one of the big challenges here. Moreover, virtualizing these accelerators and virtualizing that state is also a big challenge. And then the communication and messaging, a mantra that I've been saying for about 10 years now is it's the synchronization stupid, because it's just amazing how many of these problems just boil down to how well you do synchronization. So with that in mind, I'm going to focus on just these first two. So I would argue that there's always been this incredibly critical balance between data availability and processing. And when I first started designing processors like 20 years ago, it turned out that the CPU frequencies and the memory cycle times weren't so far off. Access to memory would take 8 cycles, and it was kind of a pain, but you kind of dealt with it. It was not, that was just part of the design problem, but it was a small amount. Well, what we've seen is that gap has been widening, and that became really obvious during the early 90s to a lot of people. I used to have a chart that showed the gap, but I dropped it out of the presentation. Well, the implication of that gap, of course, is that what was happening, especially on server workloads, is memory wait time was dominating computing. So 80% of the time you're sitting around waiting, 20% you're executing. On an average client app, it might be 30, 70, but it's still pretty bad. So the industry solution, of course, was the invention of non-blocking caches and out-of-order microarchitectures that hide some of the latencies in those non-blocking caches, and all was good. That's what that happy face means. Everybody seemed to, that worked pretty well. We're happy with that. Well, then there was sort of this software productivity crisis, also in the early 90s. And this is when a lot of the object-oriented programming really started to hit stride. A lot of the managed runtime, Java was really firing up then in a big way. And what are the implications of that stuff? Well, it turns out it's larger working sets. All of a sudden, the working sets got a lot bigger because objects, instead of dealing with just bits and bytes and small data structures, you're dealing with objects and indirection and all of these things that cause the working set to grow. And we're also getting these more diverse data types that were causing it to grow. So what was our solution? Interestingly, it was larger caches and adding cache hierarchies, because eventually that L1 cache, if you grow it too big, it takes too many cycles to access it. So you keep that relatively small and you build next level cache hierarchy. Today we see systems with 3 and maybe even 4 levels of cache hierarchies. So, I kind of joke about it, but that really is our solution to this problem. We've also done some amount of elaborate prefetch schemes. So there's been some good work there, and that helps, but it certainly hasn't been a big hammer. So the next situation that we're facing basically now is, we hit that frequency wall and we hit the IPC wall. So we're trying to figure out what do we do with all these transistors? Moore's law keeps going. Got all these transistors. What we're going to do is we're going to put down multiple cores. And in some cases, we're going to multi-thread them, right? So what are the implications of that? Well, now you got multiple working sets. You've got so many processors, you tend to introduce virtual machines into here. So you've got multiple OSs and their working sets. And you just massively increase the number of memory transactions. The sources for memory transactions just went way up. So the bottleneck, it becomes the memory controller. So our answer to this was, sometimes you can do SMP, multiprocessor cache sharing. That mitigates some of it. Sometimes you can do very elaborate memory controllers that have some pretty clever techniques for coalescing things and really timing out when page opens and closes occur and getting some benefits out of that. But mostly the answer has been huge caches. That's just. Well, we're starting to ship a design that's got a 6 megabyte cache, but L3 cache. But we've seen some of our competitors ship ones with 24 megabytes, and we've seen projections of even larger caches. So the answer, if our answer to this is always larger and larger caches, I kind of get a little worried.
24 megabytes.
I don't know what's next. This is the punchline, actually. But I do know there's another crisis coming. There's another software productivity crisis which involves programming these multi-core machines. And the answer to that programming crisis is going to be increased abstraction layers and, the other situation is the image and video as a basic data type. So those things are huge, and you get some streaming, and you can play that game a bit, but that'll only get you so far. So we get even larger working sets and even larger data types. So perhaps there's a play with the streaming data approach, but there's another technology that's out there on the near horizon that I think is just going to get forced into play because we don't really have any choice, and that is chip stacking. So actually going 3D, putting DRAM chips right on top of CPU chips or right under them either way, or putting them right next door but on the same substrate. So again, this is a really interesting area because I actually don't think there are too many other options out there. And yes, there are higher speed PHYs and higher speed memory interfaces, and that'll get us to the next bump. But at some point, even that runs out of speed. And as a shameless plug, I should say that at the Hot Chips conference this summer, I'm leading a tutorial on high-speed memory systems, and there'll be a section on high-speed PHYs and a section on chip stacking in that. Oh, good thought.
Isn't chip stacking somewhat limited by power, though? Right, in
Yeah.
that you can't get a lot of transistors switching on the top of your stack and the bottom of your stack simultaneously.
Yeah, there's a lot of challenges with chip stacking, and I would also say that there's a huge range of optimism about solving them. Some people are incredibly pessimistic, and some people are just giddy about it. But I actually think the answer is somewhere in between, and I think feasibility is right there. I think it's not so far off. So the next thing I want to talk about is the software stack and what I call a framework for innovation. Yes. Sorry.
Basically, you're running into exactly the same problem that the disk people run into, and that is that the interface is not speeding up as fast as the capacity inside the packages is speeding up. And the known solution in disk land is you have more spindles and you ignore the fact that you have 5 terabytes per spindle, or whatever the number is this week at Fry's. The other solution is to say a processor will have at most 4 gigabytes close to it, and then you move processors out with memory. So instead of putting in memory chips, put in processor memory chips, processor memory chips, processor memory chips, and you don't have a central processor.
Yeah.
You've got to scale the interface with the thing on the other side of it.
Yeah. Yeah, I think that's hopefully the audio can pick up that question, but the observation is that, the disk drive folks have found the same issue, have faced a similar issue, and, there's lessons to be learned in how they dealt with it. And maybe the idea is to distribute processors more towards the memory rather than aggregating all the processors and trying to go through a little straw to the memory. So there is a large body of researchers looking at memory and processors, or processors and memory, depending on which school you're from. The other thing, though, because that's sort of the far side of that discussion, the more real and the right here in front of us part of it is if you think about the way data centers are being built today, the most modern data centers, the constraint has to do with cost effectiveness and power effectiveness. So what they're doing is they're building out of blades. They're collecting up large numbers of blades, and they're providing a distributed computing environment made up of larger numbers of blades as opposed to one large clump of an SMP. So I think that's a form of the trend that you're talking about.
So it's a microblade. So
Yeah.
you scale by going down and buying a 10 gigabyte processor module.
Yep, and it's disposable.
As your cache goes large, the access time also becomes longer, right?
Yeah.
So it's almost the same as memory.
So the on-chip caches, they don't get as bad as memory, but it's not uncommon that they're 50 or 60 cycles these days. The other problem is the cache is no longer, like a 6 megabyte cache, is no longer a monolithic thing. It's actually multiple banks, and different banks have different latencies. So you've got that problem to deal with. Let's see, when you do the chip stacking, there's a lot of different solutions out there, but actually there are not a lot of solutions out there, but there will be, I think, over the next 4 or 5 years. You're going to see a lot of this. The latency to a stacked DRAM is actually, it's more favorable than accessing a DIMM because you're not going across connectors. You may not have to actually do the SERDES, you might not have to serialize and deserialize in order to get over there. So you just immediately start chopping out latency because of those effects. But it's a good point. Okay, so the software stuff. I like to think about, architecture has a role in the software stacks, just like it does in hardware. In fact, I think of architecture as the contract between layers of hardware and software. And that's big A architecture, classic stuff. Now, a lot of people use the word architecture all over the place, but I think this is the right way to think about it. So why is this the right way? Because it provides formalism and it provides standardization. And what that leads to is it defines compatibility. And that's really what you want to get to. You want to get to known quantities. So compatibility has been a key enabler for our industry forever and ever, and that's going to continue. In fact, history shows that viable products don't bet on wildly incompatible solutions. Again, I won't take any pot shots on competitor efforts here, but you know who they are. There's also a symbiotic relationship between hardware and software, where it's funny, the software is typically the enabler for new hardware features or new types of hardware, and the actual results that you get are dominated by the weakest link between the hardware and software. So you can have the greatest hardware in the world. If you can't get the software to enable it for the end user, it's kind of useless. And interestingly, the software value chain, people that write software for a living, they kind of value features more than hardware optimization. So you kind of have this difficult balance to strike. Moreover, I think software complexity has been driven to extreme levels. It can't continue, especially when we go to the non-determinism of multiprocessing. That really drives it through So I think architecture can give rise to these what I call the emerging layers of computation. And the question is, can we use this to simplify the programming models? So I'll motivate this by first talking about an analogy to the communications industry. So 20 or 30 years ago, the communications industry, there were a lot of different standards and kind of a messy situation developing. And at some point, the OSI, Open Standards, I don't know what the I is, but developed the so-called 7-layer model that you've all learned about in school, I'm sure. Well, it turns out, this makes for a nice picture. It was never really this clean, by the way, and it's still not this clean. But what it did do was it allowed people and companies to dive into these stacks at any level. And it really kind of decoupled the industry to attack the problem on multiple levels. And if you think about it, there's companies that just stayed down at that physical level and made their mint just there. They didn't have to do all the rest of the stuff. And other companies went after the middle stuff. And other companies are just at the application layers. So this abstraction was really, really a powerful thing. And I think it sort of has given rise to the wonders of modern networking because of that. The compute model, in some sense, is incredibly simple. Applications run on OSs, run on hardware at a very fundamental level, but we all kind of know that's not true, right? There's other things going on. There's virtualization under the OS. There's all kinds of intelligent I/O and sort of offloading onto those devices. In the case of Transmeta, they actually did this dynamic binary translation under the covers. The OS didn't even know about it and mapped it to a different type of hardware. Turns out in most processors today, there's microcode down there. Above the operating system, there's managed runtime environments. This is where the cloud computing stuff is playing out. Often people are running applications through browsers now, and there's a new layer developing there. And in fact, even above the application, there's what I don't have the right name for it, but I call it fault-tolerant meta apps, like SETI at home, for example, is an example of that. It's running an application, and it's throwing out chunks of work, and it could actually care less whether those chunks of work are done on the client devices it sends them out to, because if they never come home, it'll just send them out again. So even there's a layer above the application that's actually running on your computer that's possible here. So I think what this kind of gives rise to is what I call these layers of computation. And I don't know that these are the right layers. I really don't. But I've shown this at a couple different forums, and what I find is it's good just to kind of put it up there and get people thinking about it. there's sort of a physical layer, and below this physical, within this physical layer, it's divided by the platform layer. We don't really care how we get compatibility with x86. We don't really care how we get compatibility with other devices down there. We just care that we do. So the stuff above it just cares that we do. And you can kind of continue that thought all the way up. The OS, it doesn't really care that it's got its own hardware. It just needs the image of its own hardware. And that's where the hypervisor comes in. Applications, they don't really need to run on the OS necessarily. They need to run in a managed runtime environment that takes care of all the nasty details below that. Eventually you get into networked platforms, and now you can start talking about the networking layers that come out of this. Now, the thing is that this isn't something that is architected in a way that everybody just sort of accepts, the industry just accepts and goes with. It's sort of an emerging thing. And that's kind of the problem. I think the big challenge here, well, the observation, of course, is that as you go up in abstraction, it gets easier to program things. You're not writing code. You're connecting things. You're doing mashups, as a great example. My daughter does mashups at home. I have no idea how she learned how to do this, but she just starts connecting things together, and she's getting the job done, She's getting stuff onto her iPod or whatever it is. Ease of programming and productivity goes up the further up you go. There's overhead. So what I would say is your challenge for the summer is to think about this as, shift it from a retrospective observation into a more formal and deliberate network, because I think that is what's going to play out over the next 10 years. Now, there's some really interesting implications that come out of this. One, of course, is what I've been talking about, for the past hour, which is accelerated computing. All of a sudden, that just becomes part of the platform, and it's covered by various types of APIs to offer some decoupling. And those APIs sometimes are called by domain-specific languages to get more productivity up top. But the key thing is, we don't care how we get this functionality. We just care that it's there. Also, further up is that data center compute platform that I was referring to in response to a question earlier. There's some amazing things going on there. In fact, if you get some of the folks from Google to come over here and give a talk, I'm sure they have actually, they'll talk about the data center as the computer and the way they program and the way they think about, MapReduce is a great example. They've made it really easy for even interns to go in there, write MapReduce programs, and they're automatically sprayed across the data center, and they get amazing parallelism out of it. It may not be the most optimal, but that doesn't necessarily matter. They have the computers. They just want to get the job done, programmer productivity. So that's playing out as well. So uniprocessor performance scaling is nearing its limits. I think you've heard that from a lot of different sources at this point, so I don't think it's debatable. That's more of a CMOS statement at this point. There may be some new technologies that come up, but normally we would see what they are, and we're not seeing them yet. There are some microarchitecture concepts out there that people are still working on. In fact, I know some people in the room that are thinking about some of these really more advanced microarchitectures, but I think at least from an industry standpoint right now, uniprocessor performance scaling is nearing its limits. So Moore's law is great from an integration standpoint, but power scalability isn't tracking due to Vmin limits. So used to be when you got more transistors, you went to a new node, chances are that new node dropped the voltage. Okay, so the scalability of reduced sizes offered a capacitance reduction. The voltage was V squared in the power equation, so you kind of get a litho cubed kind of reduction in power. It turns out that litho cubed kind of reduction in power is what allowed you to use all the transistors that came from that transition. Going forward, when we hit Vmin, right around the corner, the V squared aspect goes away. So even though more transistors will be available to us, you can't possibly use them because of the power limits. This is a subtle but really important point. And if you don't get it, think about it later because it's really important. So this fact, combined with the realities of Amdahl's law, will ultimately place practical limits on the number of cores in CMPs. That's my supposition, anyway. So the demand for increased performance won't go away, customer value. We need to find new ways of offering that performance. Programmer productivity will be a first-order constraint. Deploying more power-efficient hardware structures, and again, making them approachable by the programmer seems to be a good way to do this. There's also a lot of really interesting system architecture innovations once you start getting into this space. So the bottom line is I believe the time for accelerated computing with heterogeneous hardware is here, and I hope you agree.
We've got time for a few questions.
So you started out talking about customer value
Yes.
and then quickly go down into performance.
Yes. Limits of performance.
Well,
yes.
limits of performance, implying that customer value and performance are identical. That is true to some extent, but I think people don't care anymore how efficiently they're using their machines, as long as it does the job they want done. Today, the place that matters is in video processing, games,
Yeah.
and the rest of the time you simply don't care. So why not focus on the things that add value and forget about metrics like efficiency and using all the cores and so on?
Yeah. No, if I didn't convey that, that is part of what I want to convey. What I didn't lay out here was AMD's future product strategy. But I can tell you, everything you just said plays into that product strategy. That's exactly what we're working on.
Do you want to mention the fact that there are things out there for...
Oh yeah, I have pens and brochures. Tons and tons of them, actually. So you can come up afterwards and grab them if you like. Yes, where do you go over there?
Talk about heterogeneous applications and how to sort of, divide the task
Yeah.
into threads that could be managed.
Yeah.
So I thought that the whole idea behind multi-core is to come into a new software programming model, which will allow you to do algorithm development in a more efficient way for parallel computing, which cannot be done with the current software, the way we are programming. Do you think that your architecture is still living in that programming model and not looking forward?
Yeah. So I would say it this way. There's no doubt we're entering the era of multi-core, and traditional programming technique for multi-core has been very, very difficult. For a lot of reasons, but one of them is just the testing and validation of the inherent non-determinism between threads is one of the main reasons, but there are others. It's hard enough to get the program functionally correct, let alone optimized. So there's a lot of research going on right now towards building language constructs that make it a little easier to program that stuff, automate the process of synchronization, offer runtime environments that do some of the resource management, and I think that stuff will be successful. But I also think that due to the limits of power and area, we run out of room in terms of how many cores we put on a die. And at some point, I just don't think that's going to offer the kind of value that customers want, to this gentleman's question. And I think there's other types of hardware we ought to put on those chips to offer the value. So I'm not in denial about the multi-core thing at all. That's good stuff. But I want them, are there any of them here, to deal with the problem of heterogeneous processors and resource management, as well as homogeneous SMPs.
Was 6 megabyte in your
Let's see.
6 MB, you said, and that your competitors were offering 24 MB.
Yeah, I might have said something I shouldn't have even said, but yeah, there'll be a 6 megabyte.
So my question was, you did not discuss at all the interconnect requirements as.
Yeah. Yeah, the on-chip interconnect requirements are getting very, very interesting, and that would be actually an interesting second subject to do someday. It's hard to answer. You want a follow-up question?
I'd like to make a comment on the programming model issue.
Sure.
If our value computing is a small number of compute-intensive applications, why not give up on general-purpose parallel programming and focus on application-specific domains, libraries, whatever, and just forget this impossible problem we've been trying to solve for 30 years?
Yeah. Well, I think, that's the I guess the beauty, I guess, of what I was trying to describe here is you can do either, depending on the product space you're going after. In some cases, like that set-top box thing I showed, they're all over in that red section. There are other people that want to be in that blue section. I think it has inherent limitations. I don't want to deny that it's there or that there's value there. There is, but not for all markets, certainly. And then I'm just as fascinated with the green section as I am the red section, to be honest. I don't know who was next. I think maybe you were. Yeah.
Yeah. How do you anticipate in the years ahead implicit multithreading and parallelization technologies like speculative multithreading and TLS will play into this trend we see where programmers are being forced to explicitly multithread, and how that ties into heterogeneous multi-core?
Yeah, that's a deep question. I think speculative multithreading, implicit multithreading definitely involves the use of a lot more hardware structures to kind of manage all of that. And
hardware anyway to do a lot of these application-specific tasks.
yeah, however, in these cases, like for doing video encode, I'm also talking about a 20 or 30x increase in performance, not a 20 or 30% increase in performance, which, and I know you have an interest in this in general, so I don't, you may be able to get 30%, you may be able to get 2x, but I don't think we'll ever match the kind of performance you can get from a dedicated piece of hardware. So what do I think about it? I think it's interesting, but I think really heed that power limit that I was describing earlier. Somehow you got to get rid of some of the overhead, or the bulk of that thing will kill you, in my opinion. Yes?
I kind of lump the coprocessors or the accelerators into two classes. One being the MPEG decode, the HDTV and things like that. And the other category being essentially a processor that is some evolution of GPU shader core or stripped down traditional. What else is there? I mean, how are we going to, is there any evolution of the HDTV fixed function little thing, just as the way we evolve these formerly fixed function shader cores? Or do you say heterogeneous to mean we're just going to keep throwing these really, really domain-specific things?
No, I don't want to go too far down that really, really domain-specific, because I also don't want to do 25 chips. I want to do
the HD or the video codec.
Yeah.
How would that differ than the evolution of like the GPU shader core?
Yeah, so I think what's going to happen, the evolution, and you said it well, the evolution of the GPU shader core is going to make that thing more and more general purpose and more approachable by data parallel programs. So it turns out that even some of the video stuff you mentioned is a data parallel problem that can be cast onto a next generation shader core, but not all of it. So sometimes it does make sense to have dedicated accelerators. Another interesting example, and you may argue this isn't an accelerator in the classic sense, but a good rule of thumb in dealing with networking is for every megabit per second, you need a megahertz of CPU compute power to run the TCP/IP stack. So when you're talking about a 1 gigabit per second, Ethernet stack, or the stack to run a 1 gigabit per second, you're talking about a gigahertz worth of performance. When you go to 10 gig, you're talking about 10 gigahertz. When you go to 100, you're talking about 100 gigahertz. And these are just goofy kind of rules of thumb. But what it says is there's no way that's going to play out. Something has to happen to better impedance match the network to the CPU.
That again is an example of an application class.
Yeah.
Like these, like this data parallel thing is a class of applications. Where that shader, shader is not designed to run shaders anymore. It's designed to run this class of applications.
Yep.
So I guess what I was trying to get at is other classes of networking, would be.
And networking as a class, I think the whole, and associated with networking, you've got compression and encryption and, so it's actually a really good question because that next great example isn't there yet, but I think it will come. I honestly do. Yes?
It seems as though we're addressing accelerated computing in a general purpose environment and doing everything for everyone, if you would. And in that sense, the efficiencies that come in as a result of that we're trying to somehow get around with the economies of scale, if you would. In other words, let us handle the accelerated computing and you guys do your stuff above. But economies of scale being what they are in emerging markets, one can rightfully expect the small fry, the small mammals becoming the bigger animals of the future. And in that sense, kind of trying to bridge the gap, if you would. In that sense, instead of trying to be everything to everyone at the lower level, one can imagine an optimization that's kind of reaching up, if you would. Using a platform that is inherently fast for what it is designed to do at a base level, and then working your way up the TCP/IP stack or into the applications.
Right.
And it seems to me that, especially when one gets into the data center, with all the virtualizations and all the stack additions that start getting added, there's a multiplicative effect that is coming in.
On the overhead.
On the overhead.
Yeah.
It's straight, you have one host, if you would, and multiple clients, and the clients getting virtualized, and then you have I/O virtualization happening underneath that. So I'm just curious what your thoughts might be as to a parallel optimization path that kind of commoditizes the low end, which probably AMD might not like that much. But
well, notice
then kind of goes up.
So if you're up here running, let's see, network aware application. So if you're up here running your browser and the only thing you're doing is running applications, through your browser on the cloud,
right.
You actually don't really need hardly any of this. You certainly don't need to go through all these layers. You just need to have compatibility with the layer below. And I think there will be devices that do that. I have no doubt. And in a way, that's cutting through the vertical overhead that you're referring to. So the same thing happened in networking. It's not like everybody attacked every level of that thing. Some people just said, look, I'm going to take layer 3 and below and just flatten the hell out of it.
That's right.
And everybody above me, you're good. If you're below me, watch out.
That's right.
And actually, it was usually the low end guys coming out. Because I do believe the low end eats the high end.
That it does.
Yeah. Let's see. Yes.
Speaking about low end, I'm thinking about what's happening to devices, and we have lots and lots of transistors we're not using. I haven't seen anybody seriously pursuing building asynchronous machines. So there's a tremendous power saving to be had there, and probably a performance gain, particularly if you can control capacitance well.
Yeah.
Why is that?
I think there are design automation and verification complexities that are just hard to overcome. In some sense, the industry has worked itself into a mode where, if you follow the way we've been going for the past 20 years, you have incredible tools and incredible automation at your disposal. If you veer away from that, and that's actually veering pretty far, you're kind of on your own. And you've got to recraft all that stuff. There are people trying to do it, but I think it takes away from your ability to actually offer value until you get over that. And then maybe there's a pony there. But is it get rid of clocking, are you going to get 30%? I don't know. You get the power efficiency. Perhaps more.
How many gates actually do something in each clock? It's a very small number relative to 100 million gates or whatever.
I certainly wouldn't sell it short. I think it's, I think that there seem to be bigger stakes at play here with these kind of principles. And, so I've certainly shifted my attention to more stuff like this. But I know there are people interested in that. I don't know who is next, I guess, maybe you.
So from this picture, do you think that x86 compatibility is going to be an issue for data centers? Data centers, are they going to stay x86? Or they might...
Well, x86 has a couple advantages. Other than the fact it is kind of an ugly architecture. Just get over that. My head didn't explode. I designed PowerPC parts for 20 years before I started doing x86, and my head didn't explode. So you should feel good about that. I do. I know that. Let's see. So there's the legacy software pull that continues. There's a ton of companies that develop their code on x86, and therefore they optimize it on x86. And often they port that code to work on other architectures. But as we saw with the RISC architectures, man, you had to offer so much more performance to make it worth their while to kind of support all those different binaries. So there's still this x86 compatibility momentum that's playing out. So that's factor one. Factor two is, there's a bit of a commodity economics play here. Intel and AMD can produce x86 processors at incredibly reasonable prices, and they can proliferate them. And I think that commodity economics aspect of it is really hard to overcome. Now, does that mean it will stay that way forever? No, probably not. But I think those are the two obstacles. So what we find is the data center is moving headlong into x86. I used to work on RISC processors. I think it's kind of done.
It's a follow-up question. So if you have something else, how much performance advantage you need over x86 to justify the switch?
Depends how hard the switch is. If it's just architectural, it would, we used to say 2x, but that didn't really seem to do it. So RISC had, arguably, at some point, people could demonstrate RISC had a 2x advantage, and that didn't do it. And at the end of the day, RISC was emulatable underneath x86, so that advantage went away. But maybe
Josh, you said 10x.
10x might.
But you can't do it this year. You have to do it next year, the year after, the year after, the year after.
Great point.
They're ramping every year. And can you spin your RISC part as fast as they're going to spin their x86? Because 10x is 3 years.
I want to push back a little on the claim that Jonathan's left now, the claim that parallel programming is intrinsically hard, and push back on you on the formal framework that you described. You described this back, I think it's slide before this. You described here the stack of, and then you describe arguing for a formal framework. And the reason it gets hard to program with concurrency is that the rigor of the formal structure at each level deteriorates the higher you get up in this stack. So that the software programmers are dealing with an environment that is intrinsically flawed because it lacks the rigor necessary.
I could see this could turn into a long discussion.
To program. So if that problem could be solved,
but
if the rigor can be maintained from bottom to top,
I think
you then give an environment to programmers that is intrinsically simpler, because you said it yourself. It's synchronization stupid.
Yeah.
Right. So you know what
I know the mantra.
So that I think is the reason why we're so worried about programming with concurrency, because by the time we get to this top level of application layer, our rigor is shot.
So the counter to that, just to put it out there and then we'll stop, because this could go on for a long time, I can tell, is, I don't want PhDs from computer science having to learn biology and geology and all the other sciences that want to use computers as a tool. I want to be able to couch languages and constructs in their way of thinking.
Understand where I'm going. It's not that I'm asking high-level programmers to learn rigorous logic or formal methods at the top level. I'm asking that we provide the rigorous infrastructure so they don't have to.
As it goes up. Okay. Actually, I don't object to that point.
So I'm going to take the last question here. Along the same line, the real issue here, as we go out to tremendous numbers of multi-cores and inhomogeneous machines and inhomogeneous memories, is how do we maintain the concept of atomicity across that collection of things?
Right.
The model that is implicit in this stack is a shared memory model, and that's not going to work. You have real problems having a lock that somehow got stuck in slow memory controlling something that's running very fast. And finding it is very hard. And, you know, frankly, I know from the experience I had with the Spark, barrier instructions are really hard.
Yeah.
They're very, very hard. And figuring out where you need to put them is something that takes a PhD in computer science.
So I agree down in this region. What you said is absolutely true. But I think arguably up here, you know, this is land of MPI today and other future kind of programming constructs where you really aren't dealing with a shared memory. You're dealing with an abstract concept called synchronization. But how it's implemented, there could be a gazillion ways of doing it. So I think the synchronization does get more abstract as you go up. It may deteriorate some of the formalism, to your point.
Well, MPI is not.
Well, like I said, that's just today. That's just today. Yeah.
Anyhow, thank you very much for the great talk.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.